Hello. So today, in order to understand the basics of the finite element method, we will be solving a simple finite element problem. Which is a very long historical problem. So our aim is to calculate the value of pi. Now I will do this by looking at the problem in the structural or the finite element analysis point of view. So we have an actual system, right? An actual system for us is a circle now. So this is a physical or continuum object. So this has a center and a diameter. And the way we can calculate the perimeter is as follows. So our mathematical problem is actually this. Pi is equal to perimeter divided by the diameter. So I have to find a way to calculate this equation. Okay, so in order to do that, I will do discretization. So I will divide this physical object into smaller elements, okay? And the elements that I'm going to use for this circle is simple lines. So let's say that I'm dividing this object into 8. And my finite elements are as follows. This is my first finite element. These are basically line objects. So I'm discretizing this structure by using 8 line elements. And these line elements are defined between nodes 1, 2, 3, 4, 5, 6, 7, 8. And from now on, the structure that I'm solving is actually not a circle, but a discrete version of it. So this is the structure that I'm solving. So it's the simplified version, more simpler geometry, which I can easily calculate the length of each element. So now let's do the element formulation. So since the problem that I have, or the mathematical problem, relates the perimeter with the diameter, so for each element, this is my, let's take a simple element like that. Let me just throw it in here. Let's take a simple element. And I have to relate the length of this element with the radius of that circle. This is the length, okay? Because I can just approximately calculate the perimeter by adding the lengths of each finite element. So what I'm going to do is, this angle is alpha. So if I just divide this angle into 2, I get the height of that triangle. So I can just say that. Let's call this length as L. So Li will be equal to 2 times L, but I want to write everything in terms of radius, so that will give me 2 times R times sine alpha over 2. And in that equation, alpha can be calculated by dividing the 360 with the number of elements. Okay, so I can rewrite the equation as follows. 2r will be equal to the diameter, alpha will be equal to 360. So my element formulation tells me that the length of each element is equal to diameter times sine 360 divided by 2 times number of elements. So this is my element formulation that relates the diameter with the length of the element. Now this is for a single element. Now I have to do the assembly. So in the assembly, I know that the perimeter can be approximated by simply adding the lengths of every member. So basically, I can just say that P is equal to N times D times sine 180 divided by N. Now the solution. Now the mathematical equation is P is equal to P over D, which is equal to N times sine 180 over N. And this is the approximate solution that we are looking at. And if we use N as equal to 2, then N times sine 180 over N is again equal to 2. Let's use 4 elements, then 2.8284. Let me use 2 more digits. 27 will be the pi. So I can use 16 elements, then this will be equal to 3.121445. You can increase the number of elements if you use 64, 3.1403331, and 256 elements will give me 3.1415138. So as you see, in this solution approach, the more element I use, the better approximation that I get. So improved accuracy, and the actual pi, I will just write the equations, the digits as follows, and this much. Okay, so it continues. So the more elements you use, the more accurate solution you will get. Now let's again overview what we did here. Now I have an actual structure, right? But when I do the discretization, now the structure will look like this. This is mathematically the problem that I'm solving. It's not this one, it's the idealized structure. So there's some approximation involved here. In our formulation, there's no approximation, so we can directly calculate the length of the member. And here we can visually say that as I increase the number of elements, I have improved accuracy. But for this specific problem, we actually didn't prove that, right? We can just visually say that. as I increase the number of elements, the geometry of the discrete structure or the discrete shape will more look like a circle. So by intuitively you say that the more elements you use, the better approximation you will get. Okay, so by just looking at it, we can say that. But the real problem in the finite element is, can we really say it for all types of problems, for all types of mathematical problems? That's the question. Can we increase the accuracy by using more elements? So this is a question that we should ask ourselves, and before doing the finite element solution, we have to make sure that what are the rules to obtain improved accuracy as we increase the number of elements. Here we can think visually and figure that out, but when we have more complicated problems, we have to set up certain rules so that we will make sure that we will get better accuracy as we increase the number of elements. That's very important because we have to know that. The other thing is, now by looking at this problem, the mathematical problem can be very simply defined. Okay, but we will see that there are certain cases where it is very difficult to come up with the equation for the problem that we want to solve. So what do we do in that case? How can we obtain the mathematical equation? Usually in our case it will be the differential equation. How do we get that differential equation for a more complicated cases? So these are the two important issues. Now afterwards we will start talking about the element formulation. Now once we set up the mathematical problem, once we know the differential equation that we want to solve, and once we set up the rules so that as we increase the number of elements, the finite elements that we will use in the solution will improve the accuracy. So when we set up these two rules, the next step will be the element formulation. So here I use an approximation, a linear approximation, right? I calculate the length of this line by using the things that I know, the radius and the angle. And I calculated maybe a certain accuracy by using 256 elements. So the other option is maybe use a polynomial, a curve here, and calculate the length of that curve, right? So it's a different formulation, and maybe it will give us more accurate results when we use less number of elements. So the next step is to come up with a certain trial function, a certain function that approximates the geometry that we want to model, and do the mathematical formulation, come up with certain equations, and test the performance of that trial function. So even though this is a very simple problem, it actually shows us all the steps of the finite element method. And we will repeat these steps in more complicated problems. Okay, now let's take a look at what we learned in this simple finite element solution. Now, we had a physical object and our task is to calculate P. So the first thing we need is a mathematical model. So let's put that as a note here, okay? What we learned. The first thing that we learned is we need a mathematical model. Our aim is to calculate the P value, but in order to do that, we need an equation, right? We need an equation to solve. So we need a mathematical model. In that simple problem, the mathematical model is this simple equation, P over D. Now, the question here is, how do we determine that? How do we obtain that? So is there a methodology to obtain this mathematical model. So these are the questions that we will be asking when we go into the finite element formulation. Now the second important issue is, now this is our physical model and this is our discrete model. So we determine the discrete model based on our finite element. So the second question is, how do we discriticize the physical system? How to divide it into simpler objects? And remember that in this simple problem, our finite elements are composed of simple lines, and we just approximate the length of the circular arcs are approximated with line elements. So since our finite elements are basic line elements, our discrete model looks like this. It's composed of 8 line finite elements. Now, the third question, okay, I decided to approximate the circular arcs with line elements, but how do I calculate its length? Or, in other words, how to do the element formulation? We want to calculate the length of that line, and how do we do that? And of course, we use the very simple approach. We know what the radius is. We know the angle of a circle. So by using these two information, we simply calculated the length as follows. Length is equal to d times sine 180 divided by n. So this is the element formulation. And we have only variable, a known variable here, the diameter and the number of elements. Now, the most important question here is, this will be our final question. How do we make sure that increasing the number of finite elements produce more accurate result? Right? That's a very important question actually when we go deeper in the finite element solution. How do we make sure that increasing the number of finite elements produce more accurate results? Here, it's actually just a visual inspection, right? So we are looking at the geometry, and you can basically by visual inspection say that if I increase the number of elements, I get a better approximation. So visually we can say that, and there is no problem. And as you see in our trials, when we increase the number of elements, we get a better accuracy. Maybe the convergence rate is slow, but we know that if I increase the number of elements further, I get a better approximation in pi. So basically here, in this simple problem, we just answer this by just with our visual inspection. We see it, right? Since it's a simple geometric problem, visually we can see it. But for more complicated problems, we need a mathematical background. So here there's no mathematical background. Right? We cannot just apply this to every problem that we have, because we have to make sure that increasing the number of elements should produce more accurate results. Okay, and these are the things that we will be discussing. The other thing that this approach showed us is the methodology, right? So we have a physical system here, and from that physical system, by using the existing or the elements that we decide to use, we determine a discrete solution. And then we did an element formulation. The element formulation gives us the parameter that we want to calculate for each element. And then we combine all these elements, which is actually the assembly step. Once you do that, you do the solution. So let's summarize this in a more general way. And I will just do it for a finite element solution in solid mechanics. So we can just say that a general approach for finite element solution in solid mechanics. Right, we start with an ideal physical system which we want to analyze. So I have an ideal physical system. So of course we don't analyze the actual system by using the finite elements. We generate a discrete version of that physical system, or idealized version of that physical system. So this is idealization. Usually that's the point where how we want to model the structure. We do discritization. And this step is usually named as modeling, not drawing. Okay, we have to think about the deficiencies of the elements that we are going to use. We have to think about the behavior of the structure. We have to think about what we want to model, what we want to achieve after that analysis, and generate our model accordingly. Okay. Of course, the finite elements are not just geometrical objects. Now, there's a mathematical model that is used to generate these finite elements. This mathematical model could be a differential equation that we want to solve. Or sometimes we start with the total energy of the system and go from there. And these equations usually relates deformations with internal forces. So based on the equations that we have and based on the methodology that we want to solve these equations, we have an element formulation. Okay, depending on the element formulation, it it shows how well your finite elements represent the behavior of the ideal physical system. And then what we do, we join, we assemble the elements, and we solve the equations that we want to solve for the whole system. But at the end of the day, we don't get the solution for the whole structure, right? We have a discrete solution. We obtain solution only at certain points. These points are called the nodal points. So after the discrete solution, we get results at nodal points. So this is the general solution approach in finite elements and in solid mechanics. Now, what we are going to discuss next is we start from the mathematical models. We start from here because in the previous structural analysis courses, we really talked about the modeling, we talked about the assembly and the solution of the system. Now, since we will be jumping into the more complicated formulations or geometries of the elements, here we will be mainly talking about the mathematical models and the element formulations. So regarding the mathematical models, we will talk about the differential formulation, so in the differential formulation, we try to relate the deformation with the corresponding internal forces. If you think about it in a simple beam element, we have axial deformations, bending deformations, and shear deformations. So our next task is to relate these deformations with the corresponding internal forces. Okay, so we will get those differential equations. And then we will also see the variational formulations. Because as we increase the complexity of the problem, sometimes having a differential formulation is very difficult. So you may need a different approach, and variational approach is one of them. Okay, and then at the end of the day, either you use a mathematical differential formulation or a variational formulation, you obtain an equation. So how to solve that? We will very briefly take a look at the approximate solution methods. So the ones that we will think about or spend some time is the virtual displacements, and Rayleigh-Ritz method, and here we will see that we can perform solution only for a single continuous element. So when we have multiple elements, some discontinuities in the system, using these approximate solution methods is very difficult, very time consuming. So that's why we won't be doing the approximate solutions, but we will do discrete solution. So we will discuss the discretization and element formulations for different types of structures. So our main focus will be the 1D elements, namely truss, beams, and then 2D elements, membrane, plates, and shells. So once we do the element formulation, the rest is, no, we will very briefly discuss about the modeling also, but the rest is very similar to the direct stiffness method. There is no difference in that. You do your element formulation. If you do a displacement-based element formulation, you obtain your stiffness matrix, you do the assembly and solve and get the nodal displacements. So this is a very brief summary of the first part of this course, Advanced Finite Element part.